Welcome to this class. The last class we discussed about the prove some important theorem regarding the dimension of a vector space, finite dimension of a vector space. The last class we proved that a theorem which saying that if we take a extended of a basis, if V is a finite dimensional vector space and we have to extend the basis of this. In this class we start our discussion with this theorem. Let U be a subspace of a finite dimensional vector space V. Then dimension of a U is less than equal to dimension of a V, and equality hold when this dimension is equal to U and V are the same. U is the same as a vector space of a V. So let's begin with the proof. We have to prove that the dimension of this subspace is less than equal to the dimension of a vector space V. So let V is equal to V1, V2, V and V basis of a V, because we have a given is a finite dimensional vector space. So V is a finite dimensional vector space means V has a basis, and in this basis has an element. So we have take assuming that B is equal to V1, V2, Vn is a B basis for V. Then there is a two things we have a B is a basis means B is a span. So span of a B is equal to V, and also we have a this B is the vectors in a B are linearly independent. This we can say that means the number of vectors B is we have a n. So that's why, because we can say that, so this dimension of a V is equal to, we have to assuming that is equal to n. So we have a dimension of a V is equal to n. So clearly, so this if we take this is a basis, so B is this is a basis element. So this satisfy these two conditions, and the number of element in this basis is n. So we say that the dimension of a V is equal to n. Okay, now we have to use the subspace of a V. So let B1 is equal to U1, U2, UM be a basis of a U because U is a subspace. So we take another set of elements B1 is equal to U1, U2, UM, and this we assuming this is a basis for U. Since B1 is a basis for U, so it is a linearly independent set in U, and because U is a subspace of a V, means this is clearly U is a subset of a V. So every value element of a U is also is a linear element of a V if this U1, U2, UN is a linearly independent set in U. So this means this U1, U2, M is also linearly independent set in V also. So clearly we can say that this set U1, U2, UM is a linearly, so B1 is also a linearly independent set into V. We can just say that because of all the elements of this is in V. So for all Ui belongs to U, so and also Ui belongs to V, because this set is a linear independent in U. So this is linearly independent in V also. Now by the fundamental property of a finite dimensional vector spaces, we have just in a vector space of a finite dimension n, any linearly independent set has at most n vectors. So it means at most n vectors. So at most n vectors means we can say that simply is equal to this means m should be less than or equal to n, and m is the dimension of this B1, and this is the basis of a U. So this means dimension of a U should be always less than equal to V. So by this result we can say that, so any we can say that this is equal to this in a vector space of a dimension n, any linear independent set has at most n vectors. So this means because of this, so m should be less than equal to n, that is this m is equal to, you have a dimension of U, and this is the dimension of a V. So we can say that dimension of a U is less than equal to dimension of a V. Okay, so now we have to just say that the next part is we have to prove that dimension of a U is equal to V. That means we have to prove that m is equal to n. Okay, so thus we have a B1 is a linearly independent set of a n vectors in V. So we have a B1 is a set of n vectors in V. So this is B, we can just say not B1. This is B is a linearly independent set of n vectors in V. By another, this if a vector space V has a n dimensional, then any linearly independent set of n vectors is a basis for V. So if we say that if vector space has an n dimensional, then last class we proved that any linearly independent set of n vectors is a basis for a vector space V. So this means we can, by this result we can say that hence B1 is also is a basis for V. So B1 is a linear independent set of vectors in U. So this means we can say that also this because of this we can say this subset, we can say that into this form. So this way we can say that into this form this way. This way we can say that B1 is also is a basis for V. So therefore span of a B1 is equal to V, and since B1 is a basis of a U also, so this means span of a B1 is equal to U also. So span of a V1 is equal to U, and span of a B1 is equal to V. So in this case we can say that U is equal to V whenever dimension of U and dimension of a V are the same. If dimension of a U is equal to same, then B1 is a linearly independent set of n vectors in V. And in a vector space V is a dimension, then any linear independent set of n vectors is a form of basis. So that means B1 is also is a basis for V. Therefore span of a B1 is equal to V, and we have to assuming that B1 is a basis for U, and that means span of a B1 is also U, and the span of B1 is equal to V, and then by these two conditions we can say that U is equal to V. So this complete the proof of this theorem. Now we have to move to the next very important theorem for this finite dimensional vector space. Is also called as a dimension theorem. And in this theorem we have two subspaces U and W are two subspaces of a finite dimensional vector space V. Then we have a dimension of a U plus W is equal to dimension of a U plus dimension of a W minus dimension of a U intersection W. So let's say we have to prove this. We have to we have a two subspaces U and W, and then clearly we have a vector space, finite dimensional vector space V. So we assuming that the dimension of a vector space V is equal to n, and then we also assuming that assuming some dimension of a U, dimension of a W, dimension of a U plus W, and dimension of a U intersection W. Let's begin. We have to assuming that dimension of a U is equal to, we have a M, and dimension of a W is equal to, we have assuming that is a P, and then dimension of a U intersection W is equal to R, and dimension V we have a finite dimension assuming that is a N. That again by the previous result, any subspace is a if we a finite dimensional vector space, then any subspace is a dimension is clearly, so this is U is a clearly the subspace of a V. So dimension of a U clearly we have to dimension of U is less than equal to dimension of V, and W is also a subspace of a V, then we can say that dimension of a W is also less than equal to dimension of a V. And we know that we prove a result if we have a U and W are subspaces of any vector space V, then intersection of a two subspaces is again is a subspaces. So that means we can say that dimension of U intersection W is also less than equal to dimension of a V. So this means we can say that dimension of a U is equal to M. So we can say that M should be less than equal to N, and dimension of a W is less than equal to V. So dimension of a W is equal to P, then P is also less than equal to N, and intersection is equal to R, and then R is also less than equal to N. So we are assuming these three conditions because the by the theorem we have a, if we have a V is a finite dimensional vector space and any subspace is at most is a dimension of V. So this means dimension of a U should be less than equal to dimension of a V. The previous theorem we can just say that dimension of a, if U is a subspace of a vector space V, then the dimension of U is less than equal to dimension of a V. Okay, so by this we are assuming this M is less than equal to N, P is less than equal to N, and R is also less than equal to N. So if we have to assuming that, so let because this we have to assuming this in the dimension of this intersection is a R element, so we have to assuming V1, V2, Vr be the be a basis for U intersection W. So we are assuming this is a basis for U intersection W, but you can see that we have to, there's a dimension of U intersection W is less than equal to dimension of you have a V, and dimension of a V is equal to M. So we can extend this subspace dimension up to the dimension of a N by the previous last lecture theorem. We can say that if we have any V1, V2, Vn a linear independent set of vectors, we can extend this up to the basis of a vector space V. So this V1, V2, Vr be a basis. Since this set is in both U and W, so it can be, because we can just say that this we have to assuming that V1, V2 up to Vr, this is the basis for U intersection W, and this means if this is intersection in W means we can say that simply is equal to this V1, V2 up to Vn is a basis of W means is a in U and also in W. So that means we can say that in this way we say that we can extend this basis up to U and also the basis of a W. So it can be extended to a basis for U and also the basis for W. And now you just see the dimension of a U is equal to, we have a M, and dimension of a W is equal to, we have a P. So this can be, we can extend this basis V1, V2 up to the this. So this means in this way we can extend into this form. We have a up to U. So up to U means we have to extend in this form. So V1, V2 up to we have a VR, and because dimension of a this U is equal to M, so we can say that U we can say some U R plus 1 and so on up to you have a up to you getting the UM, and also is the dimension of a W, because this is a common to the both the intersection of these two subspaces. So this means this can be V1, V2 up to VR, then we have a extended WR plus 1 to WP. So we can extend this basis up to this form. Extension is the same thing as this. We have to choosing a VR plus 1 which is not belong to the span of V1 up to VR, and then we have to choosing in this way. So by this way we can extending this basis into this form. So U is equal to, we have a span of if we extend the basis, that means U is nothing but is equal to span of we have a this V1, V2, VR, UR plus 1 up to UM, and W is equal to span of you have a V1, V2, VR and WR plus 1 up to WP. And then we have to choose any arbitrary vector. So now we claim that A is the form of a V1, V2, VR, and then UR plus 1 up to UM and WR plus 1 up to WP is a basis for U plus W, because U plus W we take a sum of these two. So that means the element of this is equal to V1, V2, VR, UR plus 1 to U, and then V2 VR and WR plus this. So sum is nothing but is equal to of the form of a in this form. This is the element of a sum. Now just you see if we claim that this set A is equal to V1 R and so on is a basis for U plus W. So if we prove that this is a basis for U plus W, then the number of elements of this is equal to, clearly you can say that we can say that this is true. If this is true, if we have just say that this is a basis for U plus W, then number of element in this basis you have a R up to this and then so on. So this means we have a R, and then you have a just this is nothing but is equal to, this is the element of a R minus M, and this is the element of a you have a R minus P like this. So this means, sorry, we have to reversely, sorry, we have to just say that into this form. So this means this, I just said that if we like this, if we prove this is the subspace of is the sum of U plus W, then this is total is R element, and this element you have a we have a M minus R, and this is the element you have a P minus R, and then dimension of a if this is a basis for this set, then we can say that this means dimension of u plus w is nothing but is equal to r plus m minus r plus p minus r. Then this is nothing but is equal to, you have a m plus p plus m plus p, and then you have a, again you can say that this is equal to minus r. So m is equal to nothing but is equal to, you know, that dimension of a u, p is a dimension of a w, and r we have to assuming the dimension of a u intersection w. So if we succeed to prove that this set A, our claim this set is a subspace of a V. So that means if this is true, then I just say that r plus m minus r, p minus r, and this is equal to this, which proves the theorem. So let's starting from this, we have to proving this. So to show A is a basis for u plus w, we must show that A is linearly independent, and the second is a span of A is equal to, we have to show that is a u plus w. So we have two things we have to proving this. This set A, we have to choosing this set A is linearly independent, and also span of this A is nothing but is equal to whole of the vector space is V. So span of a u plus A is equal to span of a u plus w. Okay, let us start. First we try to show that A is a linearly independent. If A is a linearly independent means we have to suppose the I running 1 to R alpha I Vi, because we have a is the form of a this, you have a V1 up to Vr, and then you have a ur plus 1 to you have a um, and then you have a wr plus 1 up to wp. This is the element. So this means we shall have sum of alpha I running to r, alpha I Vi, and then we have to write this element. So this is r plus 1 to m, beta ui, and then the sum is r running 1 to r plus 1 to p, wi is equal to some 0 vector. Okay, so now this can be rewrite in the form of a this can be written in the form of a, we have a like this some of these things, and then we have to take as this is out to this side. So this case is equal to minus times of this thing. So we can rearranging this, we can write in the form of a alpha I Vi, this is equal to minus this, and now you can clearly say that we have a like this, you have a element is this V1 V2 up to Vr, and then you have a ur plus 1 up to you have a um, and then clearly this this is the element of a u, and if we have a just say that this is equal to the element of a this is equal to you have a like this w of r plus 1 up to wp, and this is the element of a also is a w, and then means we can, as this is the element of a w, so we assuming this whole thing is equal to some v. So this sum is clearly is the element of a u, and this are the element of a w, and this is equal to v, because you just say that if we write this is some arbitrary is equal to v, because this v is lies in both u and w. Why v is lies both in w? Because this left hand side is in the u, and this right hand side is the w. So this v means v is equal to this, means v is the element of a u, and this v also is equal to this, v also is the element of a w. So this means if v lies in both u and w, then we clearly say that this v is the element of a u intersection w. So clearly we have to just say that. Now if v is the element of a u intersection w, so we can express as a uniquely as a linear combination of v1 v2 vr. So v is equal to, you have to write v1 1 2 r up to delta I Vi, and that means we can just say that if v is equal to this can alpha I1 to r delta I Vi, and this is equal to v, and then we have to just say that assuming this we have to be in the back side, v is equal to, we have a minus times of I running r plus 1 to p, and then we can say that into this form we have a gamma I, you have a wi, and then you have to Vi is nothing but is equal to r to this delta I. So this means we can replace b is the value of a v into this form. So this can be written in the form of this plus this is equal to 0 vector, And now if you see this is equal to 0 vector, means we have to just say that this is the vectors linear combination of the 0 vector of we have to write is like this: delta 1 you have a V1 up to you have a delta R is equal to VR, and then plus you have a gamma of R plus 1 W of R plus 1, and then so you have a gamma P and WP is equal to 0. And now you see this V1, V2, VR, WR plus 1 and WP is the element of a W, and W is the basis for a this V1, V2, VR, WR plus 1 up to WP. So we have to write this V1, V2 up to VR, WR plus 1 up to WP, and this is a basis of vector space subspace of a W. And if this basis of a vector subspace of a W means these vectors are linearly independent, and if these vectors are linearly independent means these scalars, all scalars must be equal to 0. So that means we can say that each of delta i's and gamma i's are equal to 0. So this means we can say that clearly this, because but this set of this is a linearly independent, and this set is linearly independent means each of this alpha I and gamma I is equal to 0. So if each of delta i's and gamma i's is equal to 0 means we can say that so this means we have each of delta I and gamma is equal to 0. Delta I and gamma is equal to, substituting this gamma of R plus 1 gamma P is equal to 0, we find that in this we have to just say that here so this is whole thing is equal to 0, and if this whole thing is equal to 0 means we can say that this I running 1 to R plus 1 and this alpha I Vi and this is equal to 0 sum. So we can say that clearly this sum is equal to 0 in the this way. And again these are the vectors for this form of this vector v1 v2 vr ur plus 1 up to um, and again this is a subspace of is a basis for a u, and if its basis for u means these vectors are linearly independent, and then all scalars are is equal to 0. So each of alpha i's and beta i's are is equal to 0. So this means all alpha i's and beta is equal to 0, and this implies that we have a actually this form is equal to I running 1 to R alpha I vi plus we have a I running R plus 1 to m beta ui plus sum of I running R plus 1 to P, we have a gamma I wi, and if we starting from this position, and ultimately what we show that each of gamma is equal to 0 and each of alpha is equal to 0, each of beta is equal to 0. If we taking this sum of these linear combination is equal to 0, this is a trivial linear combination. So if this is a trivial linear combination, what we say that means the set V1 up to we have a VR, and then you have a UR plus 1 up to you have a UM, and then we have a UM, and then you have a U of we have a W of R plus 1 to WP. It's linearly independent, and that means we can say that A is linearly independent. So hence A is a linearly independent, and which gives that we have to complete the proof of the first part of this problem. Now we have to remaining show that this set is A is span of A is equal to U plus W. So we have a second part. We have to show that span of A is equal to U plus W. So if proving this, we have to just this is I just take in this form we write span of A, not this span of A is equal to U plus W. So let we are assuming any arbitrary vector z belongs to the U plus W, and if z is the element of a U plus W, that means this z can be written as a U plus W. U is the element of a U and W is the element of a W. So if U can be written as the element of a U plus W, and then we can say that U is the element of a U and W is the element of a W. So we have a V1, V2, Vr and UR plus 1 up to U is the basis for U, and V1, V2, Vr and WR plus 1 W to P is the basis for W. So these two are the, we have a, this is the basis for U and this is the basis for W. So means as a basis for W, so we can write U is a linear combination of these two vectors, and then W can be written as a linear combination of we can write W is written as a linear combination of these vectors. So we have to write U is equal to I running 1 to R alpha I Vi, and I running R plus 1 to M we have to beta I and Ui, and similarly W can be written I1 to R alpha I prime, we take some different scalar Vi plus I is equal to R plus 1 to P, we take some different scalar from B is a gamma prime W I is there. So we just say that in this case this because this is a basis, so this can be written as a linear combination of these two vectors. So if this can be written as a linear combination of these two vectors, now we can write what is U plus W. So Z can be written as a we have a write this, so we can just take a this. So this U plus W means U plus W we can write is equal to sum of I running 1 to R alpha I Vi plus, and we have a sum of I running R plus 1 to M beta I Ui plus sum of I running 1 to R alpha I prime Vi, and then we have to combining these all the elements of a Vi together, because this run sum run into the this is the same. So this can be written in the form of a alpha I plus alpha I prime Vi plus I running 1 to M beta I Vj, and I plus this is equal to gamma prime Vj. So this means we can write the element, because we have a Z is the nothing but is equal to U plus W. U is the element of a U and W is the element of a W. So this Z can be written into a this form. So if Z written into this form means we can say that this that this is the linear combination of vectors in A. So this is nothing but is equal to, you see vectors of A is what, V1, V2, Vr, and then you have a UR plus 1 up to UM, and then you have a WR plus 1 to WP, and now see these are the vectors of this vector, and then this Z can be written as a linear combination of the vectors of U plus A. So this means clearly Z what we Z we choosing the element of a U plus Z we choosing the element in the form of a Z is the element of this Z we assuming the element of a U plus W, and then we have to show that this Z is the element of a span of A. This is not correct. This is a span of the, we have to note notation, some notation span of A also. This should be this is the span of A. So we are assuming the Z in the this, and then show that this Z implies that. So this means we can say that U plus W is containing into the span of A. Now reverse part is very trivial. If we have any element, arbitrary element we choose belongs to the A, and these elements can be written as a linear combination of the elements of this and this. U and so this is nothing but is equal to U plus W. So we have a trivially other part is very trivially. So we can say simply that the reverse inclusion obvious. Why? Because if we have a is containing into the U plus W, so this means this is nothing. This is clearly this means we have to using is span. This is simply is equal to, we have a span of A in the square bracket also. Some notation is using the this is square bracket also the span of A. So but I using this, so I just say that this should be in place of a square bracket we have a span of A. So this means reverse inclusion A is it's clearly this A is containing into the this clearly. So is A containing into this form, the span of A is containing this is equal to in this form. By this we can say that span of A is containing into the U plus W. So by this and this we can say that we can say that clearly u plus w is nothing but is equal to, you have a span of A, and then we can say that we prove that see, this set A is both the condition, A is linearly independent and span of A is equal to, you have a u plus w. So we can say that dimension of u plus w, the element A is from a basis. So this implies that we can say that this A is a basis for u plus w. So if A is a basis for u plus w, this implies that we can say that we have to share that this is the basis of a u plus w. So that means dimension of this is equal to, we can say that dimension of we can say that clearly if this is a, so this is clearly we can say that we have to successfully prove this, complete the proof of this. So we have to ultimately show that A is a basis for u plus w. So this means dimension of u plus w is the element of a number of element of a basis. Number of element of the basis is equal to r plus m minus r, and then you have a plus you have a p minus r, and this is equal to, you have a m plus p minus r. M is nothing but equal to, you have a dimension of a u. P is nothing but is equal to, you have a dimension of a w, and r is nothing but is equal to, you have a dimension of a u intersection w. So this dimension of a u plus w, we can prove this very important theorem regarding the dimension theorem. So this is called as a dimension theorem. So we successfully prove this theorem. So I have to stop this lecture here. In the next class, I have to discuss some problem related to by this dimension theorem, and if we have to assuming also, if we take a intersection or two subspaces is equal to a 0, then what is the dimension of a u plus w is equal to, simply is equal to dimension of a u plus dimension of a w. So we also discuss some problems, and this in the next class I definitely try to some exercises or example regarding the dimension theorem, and also the we have to one example take in the form of we have to extend the basis of all these things. Here we have to taking the subspace, we have to extend the basis of both the subspaces, and then we have to prove this theorem. So in this next class we have to explain this theorem by the examples. So I have to stop this lecture here and continue in the next class. We have some exercise examples of based on this theorem. Okay, thank you. I have to stop here.